All right. Hello, everyone. My name is Jack Moody, and this is my talk on topic modeling and latent Dirichlet allocation. Quick look at our agenda. We're starting off with an introduction to topic modeling in the arXiv dataset that we used. Then we'll be talking about latent Dirichlet allocation, otherwise known as LDA, the exploratory data analysis and data cleaning we performed to get our data in a ready state, the evaluation criteria for our algorithm, and then our results and conclusion. So an introduction to topic modeling, it's a technique used in natural language processing and machine learning to identify topics or themes that are present in a large corpus of text. The goal of topic modeling is to extract the underlying structure of a document collection, usually by automatically identifying the main topics that are discussed in the text. And when thinking about that, I immediately thought about the data sets that are in arXiv. arXiv is a free distribution of academic articles from researchers in fields ranging from physics to computer science, biology to economics. And it's a massive wealth of knowledge that can often overwhelm a first-time user to try to figure out what they actually want to learn about and trying to cluster those types of topics. So the problem statement that I wanted to see was if LDA can find the most common topics across 7,999 unique artificial intelligence papers that were found on arXiv. So now going into what LDA is, it's an unsupervised clustering technique that's commonly used for text analysis. It's a type of topic modeling that can represent words as topics, and documents are collections of those word topics. And LDA makes two key assumptions about the data that it's fed. Documents are a mixture of topics, and topics are a mixture of words that can be pulled from a corpus, and these topics use a probability distribution to generate those words. Thinking about this more visually, if you look at the top there, this is a plate view, and there are three levels to an LDA representation. There are parameters alpha and beta, which are corpus level parameters assumed to be sampled once when generating a corpus. And then we have our theta variable, which is a document level variable sampled once per document, and it's assumed to be a Dirichlet distribution. And finally, there are the Z and W variables, which are word level variables and are sampled once for each word in each document. For this algorithm, the Dirichlet hyperparameters are going to be our alpha, which is a document topic density, and beta, which is word topic density. When thinking about this from a statistics or a probability distribution standpoint, you get this equation that's on the bottom, which can look a little bit overwhelming. But starting on the left, really, that's just saying the probability that the algorithm could spit out any document. And for the right side, essentially that first piece there before the sum is kind of like the setting of our machine, if we're going to think of LDA as a machine. And that's going to be helping us find topics, and it's a Dirichlet distribution. And then on the right-hand side, after that sum, those are really the gears of the machine that is going to be helping us find words. And those are both multinomial distributions. And we can see how well our algorithm is doing by tweaking those hyperparameters, which are going to be our alpha and beta. So to do our exploratory data analysis, we started by dropping all non-relevant columns. So that's really just keeping the abstracts. And now you have these huge chunks of text. And we simplified that down by essentially making it a list and removing punctuation and case sensitivity. So removing capital and lowercase letters and making sure everything is lowercase. And we tokenized each sentence and removed the punctuation and special characters like abstracts or ampersands. And then we removed stop words, which are like the most common words in the English language. The library had 153 of them. Think about, and those types of words that are used all the time. From there, we perform stemming and lemmatization. That's essentially looking at all the different conjugations of words and making them all the same. And we derived our corpus and our dictionary and built our initial model. The evaluation criteria that we used on this model falls into four categories. One, the perplexity score, which measures how well the model predicts the new data, and you want that to be as low as possible. Your coherence score, which measures the degree of similarity between your words, and you want this to be as high as possible. And then we looked at it visually, and with some human evaluation. You always kind of need humans in the loop for these types of things to make sure your results make sense. So for our results, we did an initial look with just guessing, with alpha and beta being equal to both to 0.1, which is what was recommended for the Python library we were using. And this gave us a perplexity score of -7.9 and a coherence score of 0.393. It might not be too bad, but I wanted to see if we could fine tune this even more. So I ran it on a bunch of different estimates for alpha and beta on 75% of the data. And what we found was the best solution or the best coherence score was when alpha was asymmetric and beta was equal to 0.91. That gave us the same perplexity score, but a huge increase in the coherence score of 0.56. From there, I decided to run those hyperparameters on the entire data set. And sadly, our perplexity score stayed the same, but the coherence score went down, which was not something that I was expecting. And the only reason why I think this could have happened is somehow in the extra 25% of data that was sampled, there was a large amount of skewing data that kind of changed those hyperparameters and made the coherence score go down. However, looking at this visually, our results do make sense and pass the human evaluation criteria because with our refined parameters, the most common topics that appear are model, design, use, time, show, application, and function. And this all makes sense given that most artificial intelligence papers will be talking about showing some sort of design, model, application, or function. So overall, our purpose was to see if LDA could find the most common topics across 7,999 unique papers, and it did that fairly well. We performed some exploratory data analysis and cleaned up and got our initial model, refined those hyperparameters to see if we could get it even better. And then our ultimate results passed all 4 of our evaluation criteria, which is great. And here are my references if you have any questions. Thank you.